So welcome back again to discussion on the time-dependent perturbation theory. So today we'll discuss a semi-classical approach of the atom-field interaction. Okay, so we already know that the Hamiltonian of the atom-field interaction is take the form H is 0 plus E by mc A dot P. Okay, where H is 0 is the free Hamiltonian, the Hamiltonian of atom. Okay, and this A dot P gives the interaction term. Okay, now first of all, if you know the explicit expression for this vector potential, we can find this interaction term. Okay, now when you discuss the classical electrodynamics, what is the expression, what is the equation satisfied by the vector potential? Now in different gauges it satisfies the different equations, so we can consider the gauge that we have already used. So in Coulombic gauge, what is the equation satisfied by the vector potential? The vector potential satisfy this equation del square A equals 1 by c square dou square A by dot t square. So this is nothing but three-dimensional wave equation. Okay, now what is the solution for this? So solution, the vector potential, I can write the A of RT is some constant A0 is amplitude e raised to I k dot R minus omega t plus A0 e raised to minus I k dot R minus omega t. Okay, and there should be some polarization vector, and the polarization vector I will just denote by symbol the epsilon, the unit vector epsilon. Okay, and what is k here? So k represents the wave vector. Now in Coulombic potential, we know that your del dot A must be 0. So that would imply the k dot A must be 0. So that means the vector potential cannot have component along the direction of propagation. This vector k gives the direction of propagation. So it's a wave vector. It gives the direction of propagation. Okay, so that which means there is no component of vector A along the direction of k. Okay, so obviously, therefore, the k this vector potential must be in a single plane, a plane perpendicular to k. So A must be directed or A must be lie on a plane perpendicular to the propagation vector. Okay. Now, what is your A0 then? We can find the explicit form of A0 also. So for that, we should find the expression for the electric field and as well as expression for the magnetic field. So once you find the electric field and magnetic field, it is possible to find the total energy density U, the total energy density of the electromagnetic field. Now in terms of this U, we can find the expression for A0. Now the average energy density U can be shown that is equal to omega square by 2 pi c square mod A0 square. Okay, so I am not showing this derivation to you. Okay, anyhow, this derivation is not part of your syllabus. So if you are academically interested, you should try it. It is discussed in your textbook. So just go through the textbook and you can do it as a homework. Okay, so we are just doing, just performing the expression for the electric field and magnetic field. From that, we can find out the average energy density. Now, if the the field contains only single atom, then the energy density, sorry, not single atom, the single photon, then the average energy I can write simply h cross omega. So from that we'll get the expression for A0. So what would be the expression for A0 then? Okay, it's h cross omega is the energy of the photon divided by volume. That would give the energy density. Okay, now what would be A0? So then A0 take the form square root of 2 pi h cross c square divided by omega v. Okay, then now I can write a detailed expression for our vector potential. So the vector potential would be square root of 2 pi h cross c square divided by omega times v into e raised to I k dot r minus omega t plus e raised to minus I k dot r minus omega t times direction of polarization E. Okay. Now, what was our the interaction term and the interaction Hamiltonian or the okay, better I lose the term, the perturbation. So perturbation we usually denote by symbol capital V, and which is given by E by mc A dot B. And therefore, it takes a form E by mc square root of 2 pi h cross c square divided by omega v epsilon dot p, then e raised to I k dot r times e raised to minus I omega t plus e by mc square root of 2 pi h cross c square divided by omega v epsilon dot p e raised to minus I k dot r e raised to plus I omega t. Now this entire term I can denote by symbol small v, and this entire term I'll denote by symbol v dagger, and hence the interaction potential or the perturbation term is simply v e raised to minus I omega t plus v dagger e raised to plus I omega t. Okay, so now what is v here? So v is simply e by mc square root of 2 pi h cross c square by omega v epsilon dot b e raised to I k dot r. Okay, so surprisingly we are getting a harmonic perturbation. So if you treat your field as a classical field, then the perturbation term in the atom field interaction is just look like a harmonic perturbation. So here one of the term shows the absorption. Okay, so obviously this term represent absorption and this term represent emission. Okay, so due to the interaction between the field, the atom can go for an excited state or the atom can go for a lower state. Okay, so absorption and emission. Now we can find out the transition probabilities. Okay, so how to find the transition probability or the transition rate? We'll denote by symbol gamma. So gamma I to F. So in case of emission, so emission is characterized by the expression V. So it would be 2 pi by h cross linear product psi f v psi I whole square, then Dirac delta EF minus AI plus h cross omega. Okay, and what is the transition rate corresponding to the absorption? Sorry, I have to rewrite it. Is e raised to minus I omega t stands for emission, and this stands for absorption. Sorry, what I said the earlier was correct. So this stands for absorption. Is e raised to minus I omega t stands for absorption, because what would happen, this will leads to EF minus EI minus h cross omega. So that stands for absorption. Okay, so therefore here it should be V dagger then 2 pi by h cross the inner product psi f v psi I whole square delta EF minus EI minus h cross omega. So this would be non-zero when EF minus EI minus h cross omega is 0. That is EF is equal to EI plus h cross omega. So that is why it is called the absorption term, and this stands for emission term, and this would be V dagger, because the e raised to plus h cross omega, e raised to plus h cross plus omega comes with V dagger. Okay, so there is a slight change in our previous discussion and the present discussion. I think you can able to follow it. There is no much issue. Okay, so if you want, we can define this as V and this as V dagger. That is also no issue here. Okay, now what is V? So we already defined. So therefore, this become 2 pi by h cross. Okay, so this is your V. So better take this next measure. So E by MC E by MC, then 2 pi h cross C square by omega V whole square root. Then epsilon dot P or mod square. Then Dirac delta EF minus EI minus h cross omega. Okay, if you want, we can simplify it. So anyhow, the important thing is we can get the absorption and as well as emission. The absorption depending upon this entire term, and the emission depending upon the V dagger. And I can explicitly write what is the expression for V dagger, and we can write uh, the rate of emission. Okay, so that's it about the discussion of semi-classical theory. of the atom field interaction. Now, the one of the important point that we have to discuss here is for the absorption and as well as emission, we need the field. Okay, so that is the main takeaway. So the semi-classical theory concludes that for emission and as well as absorption, the presence of field or the presence of external field is necessary. So that is, if the vector potential is 0, then the transition rate for emission would be 0 and the transition rate for absorption would be 0. There will not be any transition at all. Okay, but there is some problem here. We know that the excited atom can emit. So such kind of emission is called the spontaneous emission. So therefore, I can say that the semi-classical theory fails for explaining the spontaneous emission. Okay, so we need the quantum theory of radiation. We need the quantum theory of field in order to understand or in order to explain how the spontaneous emission occurs. Obviously, this the semi-classical theory is enough for the absorption and as well as stimulated emission. We can explain it. Somehow we can explain it, but it fails in the case of the spontaneous emission, which is a ubiquitous phenomenon. Okay, so we can stop our discussion on the semi-classical theory of atom field interaction here. In the next class, we'll discuss the quantum theory. So first of all, we have to quantize the electromagnetic field. I will give a just overview about the quantization of electromagnetic field, and thereafter I will discuss the quantum theory of the atom field interaction. Okay, so thank you everyone. We'll see you in the next class.